Hello, this is the second video presentation. In this problem we have a combined loading problem, which is basically a culmination of everything we've learned so far from bending, transverse shear, axial loading, and such. So in the given statement, the problem statement, we says find the principal stresses and the maximum shear stress at point H being this little block here. I've already created the free body diagram from the given diagram, and this just makes things a lot simpler without having a reaction force on the wall. And all the dimensions are given, and then diameter was given as 1.5 inches. I went ahead and said that the radius then would be 0.75 inches. Let me fix my light here for you. All right, the first thing you want to do for a problem like this, you want to create a table that combines the loads, and then R being their position, I, J, K. And this just being in terms of X, Y, and Z would be the X direction, Y direction, Z direction. And then the forces, I, J, K again. And then the moments, which are caused from said things, I, J, K. So as you can see, the certain loads that we were given a 100-pound load here, 100-pound load. Also given a 175-pound load and a 125-pound load. Now, what do you want to do here? You want to just get their location with respect to the point H. That being for the 100, 18 inches, 8 inches, and then 0. Here, let me separate these. For the 175, that would be 12 inches, 0 inches, and then 10 inches. And you can see 18 is just got from adding 12 and 6, X direction, 8 up in the Y direction, so on and so forth. And the 125 also acts on this 18 and 8 inch thing. And then the forces, this 100-pound, it acts in the X direction, so it'd be 100 on the Y, I, 0, 0. The 175, that acts in the Y direction, so it'd be 0. And it's also negative because it is going in the negative direction with respect to the given directions. Up is positive, down is negative. This would be 0, this would be 0 down here. Okay, you can see 125, it's also going in the negative Z direction, so it'd be negative 125. Now, what you want to do is you want to cross R with F, and then we'll give you moment. So basically, it just gives you what these certain forces, what they're causing the certain points on this to do about the given axes. So for the first one, you'd cross 18.8 with this 100, you get 0, 0, and negative 800. Now this makes sense, negative 800 in the Z direction, because it is pulling here, so it'd make it rotate about the Z axis clockwise, so it's negative 800. This one here would be 1750, 0, 0, 0. And then if you move down here, get negative 1000, 2250, and 0. So now, with your given forces, given moments, you'll be able to add all these together. And what you want to do is, sorry, that was my roommate. You want to find the reactions. And the reactions, what they are is basically what H does to counteract each of these, either be it forces or moments. So the reactions at Rx equal negative 100 pounds, because you know, if it acts 100 in the positive, it reacts in the negative way. Ry equals 175 pounds. Z equals 125 pounds. And then Mx. When you add these together, you get positive 750. So the reaction would be negative 750 inch pounds, because you crossed it, inch and the force. My equal negative 2250 inch pounds. It's just the negative of this one. Then Mz would equal a positive 2900 inch pounds because it's just the addition of these two. Now, another very important thing that you need to know is you need to find the longitudinal axis from this, and in this case it would be the x-axis. And you know this because when you apply a force on this axis, you will get axial stress, which basically means you either get compression or tension. So it's trying to like squeeze this pole down or expand it. So when you do that, you get Rx, that is your axial stress. Now this will help you find the compressive or tensile strains on this point H here. So when you do that, you want to create a small diagram of what you're seeing. And this is a cross section of the thing. Now this is the point H. Now I chose to look at this from the Z direction just because it makes it like you need to be able to see in which way the x-axis is going so that you can determine which way this reaction force is going. And this would be the Y. I could also look from the Y direction. I just chose to do the Z. It doesn't matter. And then since this is a negative 100, it'll be coming out like such, 100 pounds. And then because of this, because it's pulling, that'll be this point H here will be in tension. So when you go to write the stress of this, it's in the X direction. You get your force over your cross-sectional area. Now with your force, it's in tension, so it's positive, 100 pounds over the area, which is just pi r 0.75 inches squared. When you get this, it comes out to a value of 56.588 psi in tension, so it's positive. Now what you want to do here is create stress blocks, and these stress blocks, what they do is they show you what this axial stress is doing on given planes. So I'm just going to write the planes that have the x-axis on them, because that's the direction in which this force is acting, or the shear stress, the axial stress is happening. So x, y, this is your stress block here. It's moving out like such. Then I'll also make an x and z like such, x-axis, z-axis. So these, and this is acting in this direction. Both these equal 56.588 psi. Now you can see that's true because if you look, say, on this y-x axis, like I wrote down here, this thing is getting pulled out like this. So this force is acting like this, and it's pulling out on this. Now, another reason why the longitudinal axis is important is because it also tells you it's on that axis is also where torsion occurs. And what torsion basically is a twist. So in this, if you were to twist it in a certain way, that would be this thing twisting. So when I get this, and this helps because it helps find the shear that is happening on the given axis. And then when you do that, you get here torsion. Now when you do this, you want to look down the x-axis, the longitudinal axis. And here you have the y direction, here you have the z direction, and then h would be located right here on top. And then from the last statement, you see that the moment about the x-axis is negative 750. And in that case, it would be a clockwise direction. 750 inch-pounds. Now, the equation for torsion. And this would be on the xz axis because it is acting on the z and x plane, on the zx plane. You have T, which would just be your torsion force or torque, what I call it. You have rho, which is just the radial distance to outermost fiber. So basically it's just the radius from the neutral axis up to the the point that you want to look at, which is h for us, so it's at the very end, which is just the radius, over j, which would be equal the polar moment of inertia. So basically, this differs from the regular moment of inertia because it describes materials' resistance to torsion and torsion only, not like something like bending or shear, like shear stress or transverse shear. It's all about torsion, so twisting. And then when you do that, as I said, this is clockwise, so it'd be negative 750. The torque's negative 750 inch-pounds. Rho, 0.75 inches. And now J, you can find this online, you can find this anywhere. It is equal to pi over 2 of the radius of the cylinder, inches, to the power of 4. Then when you get this all out, xz, find that the shear, the torsional shear that occurs here is negative 1131.7 psi. Now, as you see, xz axis, you can write an xz shear block as such. X Z. And now, since it is negative, you gotta write your thing accordingly. So this would be going in the negative x direction, positive z. This would make it negative. This would be going in the negative z direction, positive, indicates negative. And then this here would be 1131.788 psi. Next, if we looked at Ry, so the force acting on the y-axis, you'll see that it is transverse shear. And basically what transverse shear is, say if I was to like bend this here, it would be the slippage of every horizontal axis in this pencil. It would be them slipping against each other like such when a certain load is applied, like so. So when you look at that, again, you want to make a cross-sectional area. So I do line. And then, since it's Ry, you want to be looking at it from like the Z or the X direction. I chose the Z, makes it a lot easier. Gives us this view. Sorry, it's the wrong way. It's got to be like this, sorry. H is up here. Y, X. And then when you look at the Ry, it is 175 pounds positive, so it's up here, 175 pounds. Now, the equation for this would be equal to, so the transverse shear on the XY plane, XY because YX, looking at that plane, equal V, which is just the shear force, this 175, and then Q, which is interesting, it's the area calculated from the point to the outermost fiber. I'll come back to that in a bit. I, moment of inertia, so it's the material's resistance to doing those the planes shearing like such. And then T, which is just the thickness. Now the thing about Q, when you look here, H is already on the outermost fiber. So there is no area from the point of interest to the outermost fiber. This would mean V times 0. All of this would equal 0, all because the H is on the outermost fiber, so it doesn't experience transverse shear. It is too far away from where the slipping would be relevant in any way. And the same can be said about the moment about Y. This would be bending. I'll show you in a second why that is. I'm gonna draw your thing. And then if you want Z axis and your X axis, you want to be looking through the Y axis. This would then mean the H is right here along with the X, and this is acting, and from the past thing you'll know that it is 2250 inch pound. So you can see negative 2250. That's why, actually it should be going the other way, sorry. Or no, that's the right way, sorry. Negative. Wait. Yeah, it should be going clockwise, sorry. But in this problem, it doesn't matter. Because when you look at the bending equation, you have that force, which equals m, which is the moment, y, which I'll explain in a bit, I, again, moment of inertia, y is the distance from the neutral axis to the outermost fiber, and of course, as you can see here, the point of interest, again, is on the neutral axis, so this y then just equals 0, meaning there is no force on here. That means nothing occurs due to the bending. Nothing occurs to point H due to the bending caused by moment about Y. So this would just equal 0. Again, everything we're doing here is trying to look at the reaction forces on point H, trying to see what these loads are doing to that point. And then next we'll want to look at the RZ force, which again is transverse shear. Now if you like this, I chose to look from the y-axis. This is out here. This is x. Then up here is z. And then we have this positive reaction, 125 pounds. That is acting in this direction, 125 pounds. And then again, we write the equation. And this is happening on the xz plane, as you can see. V, Q, over IT. Again, the force, this is the area, moment of inertia, thickness. Now we have here 125. Now Q, I'll find that in a bit. Moment of inertia, that's also given in multiple textbooks and whatnot online. For a cylinder like such is pi over 4 times the radius, 75 inches, power of 4 times the thickness, which would just be the diameter of the pipe, which would be 1.5 inches. Now, to find Q, the equation, so when you look at the end here, I'll just make an end view. H would be right here, and you can think of it as just a point. So you want to find everything up to this area here. What that will equal is Q, which equals y bar prime times A prime. And basically what this is, y bar equals the distance from this neutral axis to the centroid of this point. And A would equal the area of the point to the utmost fiber, so just the area of a half circle here. And then for this circle, this would equal 4r over 3 pi. Area, 1/2 pi r squared. Then, plugging in the value, 4r, 0.75 inches over 3 pi, 1/2 pi r, 0.75 inches. Square that. When all this is done, your Q will then equal 0.28125 inches to the 3. Now when you plug this back into this here, you get 0.28125 inches third. This then makes, or if you heard that again, another roommate, this will then equal, this will have a value of 94.314 psi. Now this is happening in positive, so here I'll draw a little stress block here. It is only happening on the ZX plane, so I'll only draw that one, X, Z, your bar here. Now this is positive this time, so positive Z, positive X, negative Z, negative X. And this equals 94.314 PSI right there. Now, I'm gonna use this paper. Now it's time to look for bending caused by the moment about Z. Since it is not the longitudinal axis, it would be bending. And here I'll explain what this bending does after I draw this diagram. So this would be the X direction, this here, Y. Then when you look at MZ, the reaction, it's 2900, positive, so it'd be counterclockwise. Acting as such, H would be here, and this would be 2900 inch-pound. Now basically what this bending is doing, say I were to bend this in the direction this moment is giving us, bend like this bottom half here of the pencil would be experiencing compression while the top is experiencing tension. That is because this moment is pulling on this H while pushing on this bottom half here. So that would be creating a tensile stress on this block H here. The equation for that, as I've stated before, is X of the moment, and then the Y, and the moment, positive. It's in tension, so it's a positive, creating a positive shear on this, or a positive stress, sorry. 100 inch per pound. Y, which would be 0.75 inches. Again, distance, neutral axis to the point. It's at the outermost fiber, 0.75. And I would again equal pi over 4 times 0.75 inches to the 4. This then makes a stress of 8,752.34. And of course, again, tension. Now this is like one of the bigger stresses. Now let's write the blocks with X in them. X, Y, down across. Put it in tension. X, Z. X. Put it in tension. Let's equal 8752.343 PSI. Sorry, it's a little bit messy, but that's that. Now, for the fun part, we must combine everything that we've used from every single axis, and we must combine it to find the principal stresses that are occurring on point H. So basically, it's the max tensile and maximum compression forces that are being experienced there, and also the maximum shear stress, which would be the maximum shear stress occurring at that point as well at the angle of 45, because that's where max shear occurs. So combined. Now for all the combined, we'll get the X, Y, put a shear block there, X, Z, right there. And one that I haven't written out, but I'll write it right now, is Y, Z. I'm telling you now, this won't experience anything. We haven't found any stresses that act on this plane, shear or tensile or compressive. But on the XY plane, we have experienced two. All right, sorry about that. My phone ran out of storage, but as I was saying, we've found that there is a combined tensile stress in the X direction. When you add up all these, this value here and this value right here, you find that these end up equaling 8,808.928 PSI. And then there's also a transverse shear occurring on the XZ plane. And after adding everything up, that will equal a, as you can see here, a negative value of 37.454 psi. Now, using Moore's circle, we can find the principal stresses. These principal stresses, again, as I said, are the maximum tensile and compressive forces that are, or stresses that are being experienced by this. And the equation is given by stress about x plus stress about z over 2 plus minus square root of x minus z over 2. Square all that. Add shearing stress. Now, when all these are given, you get a value of 8.928 plus 0 over z, or sorry, divided by 2 plus minus 0.8808.928 minus 0 over 2 squared plus this negative 1037.454 squared.
What?
Sorry again. So I was saying it's this negative shearing stress occurring that we saw here. And then when all this is equated out, you'll find that the first principal stress is 8,009.5 psi. 2 equals negative 120.5 psi. Maximum shear stress equals 4,525 psi. Now it's important to note as well that this is all happening on the XZ plane. And that's easy to see because when you go back to this picture here, H is on the very top of this pole here. And just so happens when you look straight down at that, you have the Z, X plane. So it all makes sense there. So these are your maxes there. Thank you.